as close as you want. And 8 is a very, very small number. So that number is not negative 1/9. How do I make this an equal sign? Limit and let h go to
0.
And that's how we get another point on the tangent line. Now I will make it straight. But you will know that I will chastise you if you write that. Because that's not true. You will have to say limit as h approaches. And don't drop it here or another point either. And now, when h goes to 0, this is going to go to, well, you learned something about limits in calculus. Negative 1 squared. Which would be the derivative where?
X equals 3.
What if we wanted to find the derivative at 4? Well, now. You have another number you would like to find the derivative at, sir. X equal to 8. We are going to find the derivative at x equal to? We are going to find the derivative at x equal to? X is 8, okay? Remember that. X is 8. What? X is?
8.
8. X is? 8. I'm sorry, what is this?
That's just
Okay, okay. There is your derivative. The function that will give you the slope on the function f equals 1 over x at any x. Because well, x was 8. Okay. And now you know what we did. What function in our hand? 1 over x. You have to play this game with every function. That's what we call limits, and you did it 3 or 4 times. And you might probably did it 10 or 15 times, 1 over x. It's Square root x. Oh, yeah, square root x was nasty. You had to rationalize the square root and all that nonsense. Huh? Right, Miss Yasmina? Rationalize it. That's how you do it. Yeah, you have the common denominator. That is the derivative problem, the slope problem. And of course, how do we get out of this mess here? Mr. Howard?
Rules.
Correct. The alternative is to doing it by limits all the time. Until you realize a few things. You realize that when it's x squared, it's 2x. When it's x cubed, it's 3x squared. We'll talk about that. Okay, then there's the integral problem. No, I make no apologies for lecturing. Please don't tell the dean that once he can fire me. Because it's review. So really, when we're doing limits here, we're doing this nonsense here. The derivative of the function in your hand, and it can be any old function, at any point, it can be any old x, is, the limit is h goes to 0 or f of x plus h minus f of x over h. So that's what this means. And then we have the area problem. We know how we're going to do that first. We're going to do the Riemann sums. Yeah? We're going to do these Riemann sums and then let the delta x go to 0 and add 1. Area problem. The area problem. So we did some Riemann sums last time, right? Mm-hmm. Yeah. Well, what you do is you have some function, and you want to find the area from A to B. Hmm? Exactly. And we will denote that by this. What that means, I don't know. It means this thing here. That's the way I interpret the meaning of this thing here. Why we write it like that? If I have time, I'll explain it to you. But this is this area under the function f of x between b and a exactly we give it a name. Now you say, well, you know, this is what do we do here? I mean, this is a strange nonlinear curve. But how do we find this exact area? So we say, well, you know, break it up into some rectangles, and use the rectangles to approximate the area. Because finding the areas of rectangles is easy. You just take the height and the width, and then you just need to add them all up. And you find the height by using the function. Next one, x2, x3, so you say, what is the height here? F of x1. That will be the height of that rectangle. And what's the thickness of that rectangle? It's called delta x. It will give the same delta x. Why would we want to do delta x? I don't know. And what is the height here? F of x2. And what's the thickness? Delta x. So the area is approximately f of x1 x1 delta x plus f of x2 delta x plus f of x3 delta x all the way up to f of xn delta x. And you're keeping in mind that you can take delta x out of the common factor. And then, of course, you can write that in some notation. So this is approximately. And of course, your delta x is what? What is your delta x? You take your b minus an a and divide it by n. And this was 10, and this was 2. You do 10 minus 2, and if you want to break it up to 20 intervals, 8 over 20 is delta x. Well, we need the same one. What's x1? A equals delta x. Put that into the function. What's x2? A plus 2 delta x. Put it into the function. Multiply by the thickness. Add them all up. Okay. We did some examples last time.
We did x squared.